Now we are going to discuss another fundamental result in number theory known as pigeonhole principle or Dirichlet box principle. The statement is quite simple. It can be explained as follows. Suppose that there are m pigeons and n holes. And suppose in addition that m is greater than n. That means that number of pigeons is more than the number of holes available on the roof for them to stay. So naturally, if all these pigeons have to stay in the holes, then at least one hole must be shared by more than one pigeon. That is, at least two pigeons must be there in one or more holes. So the precise statement is the following. Suppose there are m pigeons and n holes with m greater than n, then at least one hole has more than one pigeon in it. So if we convert this into our own language, classroom language, maybe we can say something like this. Suppose that there are 10 benches and suppose that there are more than 10 students, say 15 students, then naturally not every student can have his own unique bench. Every student will not be having his own or her own bench. So more than one student or at least one student must share a bench with another student. So this is what basically pigeonhole principle says. If you want to prove this, the proof is quite simple and it uses the method of contradiction. So we are given m greater than n and we are given that there are m pigeons, n holes. Now suppose that no hole is being shared by any pigeon, therefore all the m pigeons require at least m holes. Therefore the number of holes, since all pigeons are having their own holes, number of holes n must be greater than or equal to m. So we are repeating the argument once again. Suppose that no hole is being shared by any pigeons. That means that there are m pigeons and all the m pigeons have their own holes. Therefore, there must be at least m holes. So number of holes must be greater than or equal to number of pigeons. So n is greater than or equal to m. But it's already given another statement. What is that? N is less than m, but these two cannot go together. N is less than m and n is greater than or equal to m. These two cannot go together and therefore we are arriving at a contradiction. So what we assumed must be wrong. That must be, that is that, what did we assume? We assumed that n is greater than or equal to m, and we assume that to arrive at that n greater than or equal to m, we assume that not a single pigeon is sharing a hole with another pigeon. Therefore, that assumption is wrong. So at least one pigeon must share a hole with another pigeon. That's what the pigeonhole principle says. Now, only that much about the pigeonhole principle. Now we have one notation. We suppose that we are given two integers a and b. We say that using division theorem, we say that b divides a or b is a factor of a or a is a multiple of b. All these are equivalent. B divides a or b is a factor of a or a is a multiple of b if we have a is equal to bq for some q integer. So that means that in the division theorem, A is equal to BQ plus R. Here we have A is equal to BQ plus 0. In this case, we say that B divides A. For example, we have 25 is equal to 5 into 5. So 5 divides 25. Now 24 equal to 6 into 4. Therefore, 6 divides 24. 4 also divides 24. But 24 equal to 7 into 3 plus 3. The remainder not equal to 0. Therefore, 7 does not divide 24. So these are some examples of showing that what we actually mean by saying that B divides A, or B is a factor of A, or A is a multiple of B. Now we will move towards some more interesting results using the pigeonhole principle and using the division theorem that we have just now proved. Now we will see an application of the pigeonhole principle and the division theorem that we have verified. So before going into the exact statement of the application, we will try to see it using an example. Suppose that we are choosing a positive integer greater than or equal to 2, and we call it to be b. Suppose, for example, we take b to be equal to 3. Now take at least 4 randomly chosen integers. Maybe we can take 4, 7, 10, 11. Now consider the differences between these integers. That means take pair of integers and take their difference. So if you take 4 and 7, we will be getting minus 3. If you want, we can just rearrange it so that we are only supposed to take difference. Since we are interested only in division with b, we can take the difference in either way, either 4 minus 7 or 7 minus 4. So we take 7 minus 4, we will get 3. 10 minus 10 minus 4, we have 6. 11 minus 4, we have 7, etc. Now, the observation here is that 3 is a multiple of b. Remember that we have chosen 4 integers randomly. 6 is also a multiple of b. So, the claim that we want to make is rigorously the following. Suppose that we are given, so statement is this. Suppose b is a positive integer greater than or equal to 2, choose b plus 1 integers randomly, then at least 2 of them, at least 2 of them will have their difference divisible by b. This is what we want to prove. As I told in the beginning itself, we are going to make use of the pigeonhole principle and division theorem for verifying this fact. Suppose b is, as given in the question, suppose b is greater than or equal to 2, and choose b plus 1 integers randomly, and suppose that these integers are a1, a2, etc. a, b plus 1. Now we want to say that at least a pair of them will have difference divisible by b. So what is meant by pair of them? That pair can be a1 minus a2, that pair can be a2 minus a3, a4 minus a5, etc. Whatever pair you are choosing, it's fine, but we want at least one pair to have difference a multiple of b. So to observe these, so just remember that we have b plus 1 integers, and if we divide each of this number by b, then we will be getting remainders from 0 up to b minus 1. Therefore, if ai we write as bqi plus ri, the ri's are going to lie between 0 and b. Therefore, ri can be 0, 1, etc., b minus 1. So how many possibilities are there altogether? There are only B possibilities. If there are only B possibilities, that means that see, we have A1, A2, etc. A, B plus 1, and each of them we are writing as BQ1 plus R1, BQ2 plus R2, etc. equal to BQ B plus 1 plus R B plus 1. But we don't have B plus 1 integers as possible remainders distinctly. So that means that at least two of the remainders here must be the same. Say R K and RS must be same because we have only distinct B remainders possible and we have listed here B plus 1 integers. Therefore, at least two of them must be the same. Therefore, AK equal to BQK plus RK, AS equal to BQS plus RS, but it is the same as BQS plus RK. So if you take the difference of these two, what will you get? Therefore, AK minus AS is going to be B into QK minus QS. Therefore, B divides this difference AK minus AS. So we have verified our claim. Therefore, if we choose B plus 1 integers randomly, at least one pair of these integers will have their difference a multiple of B. We stop here. Thank you.